Yeah, so when adding and subtracting, if you have the same powers of two numbers that you were adding or subtracting, you just subtract this part. But if you are subtracting or minusing power with different digit values with different powers, then we'll have to go by this. The number that you're gonna choose is whether you want to make this one become the same power as this one, or this one become the same power as this one. Same applies to this one, depends on your choice. But before adding or subtracting, you have to have same powers if they are different. Now let's do this example. Add 3.28 times 10 to the power of 3 in this one. So in order to add, it says we're gonna have to put them in the same decimal by putting one of these two not in a scientific notation form. So for this one, we choose this one so that it will have the same power as this one, and we'll do our calculation. So we have 0 plus 2.5. Okay, now they have the same power, so we'll just add them. 10 to the power of 5 is equals to, we'll have our answer will be 2.10 to the power of 5. Yeah, so that's our answer. That's how we do in. Yeah, so the same applies to subtraction. We'll have to make these, either this one or this one will have the same power. Let's make this one has to have the same power as this one. Notice this one is not in standard notation, whereas this one. So now we can go ahead and do our maths. That's, since we have the same power, we leave them out of the bracket, times 10 to the power of 2, and we minus 42.3 minus 9.56. Since it has the same power, we leave it out of the bracket and we do this. We do our maths by subtracting this from this, just by the way it is. We have 32.27. Once we have 32.27 times 10 to the power of 2. So yeah, that's our answer for this notation. Okay, when multiplying numbers written in scientific notation, multiply the first factors and add the powers or the exponent. So example, it says multiply 3.2 times 10 to the power of 3 and 2.1 times 10 to the power of 5. So we multiply the first factor and then this one, and we add the exponent. So yeah, we add the exponent. So when we do that, we have 6.72. We add the exponent with negative 3 plus 5. We have 2, so our new exponent is 2. Now our answer is 6.72 times 10 to the power of 2. That's our answer. That's basically how we do it when we multiplication of scientific notation. Now dividing. When dividing, we divide the numerator by the denominator and subtract the exponent in the denominator from the exponent in the numerator. So example is given 6.4 times 10 to the power 6 by divide 6.4 times 10 to the power 6 by 1.7 times 10 to the power 2. So that's how we do it. So it says when we divide, we subtract the exponent in the denominator from the exponent in the numerator, and we divide this. So when we divide this factor alone, first we leave this one out. Okay, that's 6.4 times divide 1.7, we have 3 point. We subtract the denominators from the numerator, so 6 minus 2. Now our answer is 3.76 times 10 to the power of 4. So yeah, that's basically how we do it, how we deal with division. Our next subtopic of discussion is order of magnitude. It's a topic where it's under measurement. So yeah, when dealing with very large or small numbers, we often interested not in how exact they are, but only in their approximate magnitude. So in every measurement, error is involved. Which error we're gonna discuss about it in the future videos. Error is involved, so we only take the approximate magnitude. Yeah. So the order of magnitude of a number is the power of 10 closest to that number. So the rules to find order of magnitude is, to find order of magnitude, it must first be written in scientific notation form. That's the rule. And if the number A is less than 3.16, then the order of magnitude is 10 to the power of B, which means the power remains as it is. And the second part is, if the number of A is, if the number is, the A is greater than or equal to 3.16, then the order of magnitude is 10 to the power of 5. That's this part here. Is B plus 1. We have to add 1 here. The reason for this is that 10 to the power of 0.5 is 3.16. Let's do the following examples. We have 5 examples here. So it says, write the following, their order of magnitude. So first one, we have 1.0 times 10 to the power of 5. So let's go back to the rule on how to write. It says, if A is less than 3.16, then you leave the power as it is. So the order of magnitude for this is 1.0 times 10 to the power of 5, because it remains the same as this one, because this A here is less than 3.16. For this one is 2.4. A is less than 3.16. So the order of magnitude remains the same, 10 to the power of 3. For this one, it is same as 3.16. So we have it is equal to 3.16, so it is greater than 3.16. So we'll have 3.5 times 10 to the power of 4. Notice we'll have to add 1 here. So now our order of magnitude is 3.5 times 10 to the power of 5. For this one, we have 6.5 times 10 to the power of 7. So A is greater than 3.16. So we'll have 6.5 times 10 to the power of 7 plus 1. So now our new order of magnitude is 6.5 times 10 to the power of 8. The last one, we have 7.3. That is the value of A that is greater than 3.16. So we have 3 times 10 to the power of minus 5 plus 1. And now our new order of magnitude is 7.3 times 10 to the power of negative 4. that's basically how we deal with order of magnitude in a measurement. Our next topic of discussion is metric prefixes. It is revisited. Okay, in our previous video, which is the base number for the base multiples for the metric system is 10. So because the metric system is based on multiples of 10, prefixes can be used as to reduce the need for writing the power of 10 in a measurement, so that we make our measurement simple and calculation easy. For example, the measurement of 3.2 times 10 to the power of 3 meters can be written as 3.2 kilometers, where this one 3.2 km, this 10 to the power of 3 has been substituted by this kilometer, that kilo here, sorry, that kilo, the prefix is kilo here. Example, we have some examples here. We have milli is a prefix of measurement, and the abbreviation is m, small letter m. Okay, for example, we have this measurement here, so 4.4 times 10 to the power of minus 3. So milli has the power of 10 to the power of minus 3 here. So our metric symbol now, we have 4.4 milligram. This 10 to the power of 3 has been replaced by this milli this year. Okay, micro has 10 to the power of minus 6, has a power 10 to the power of hecto is 10 to the power 2. They have this. So the same abbreviation for micro is mu. This is not u, it's mu. It looks like u, but it's called mu. And for example, we have this measurement here, which in metric symbol now, that this power has been, this notation has been replaced by this micro here. So now our new measurement is 6.24 micrometer, and hecto, it has power of 2, so the abbreviation is h. And for example, we have this 2.22 times 10 to the power of 2 second. So this 2 has been replaced, this 10 to the power of 2 notation has been replaced by hecto here, the prefix hecto. So now our metric symbol measurement is 2.22 times hecto seconds. Yeah, so that's basically when dealing with prefixes. Second last, the topic of discussion in this video is the conversion of units. Okay, on occasion you may be expected to convert a metric measurement with one prefix to a measurement with a different prefix. Like, for example, you may be asked to convert centimeter to meter or liters to milliliter and all this, changing from one prefix to another prefix. Then you have to do this. Okay, for example, convert the following into their respective units. So we have this example here. It's just two examples. That's A is 3.2 kilometers to millimeter. So one notation to remember: when you convert from bigger unit to smaller unit, you multiply, and when you convert from smaller unit to bigger unit, you divide. So kilometer is bigger unit and millimeter is smaller unit, so we're going to use multiplication in here. And here we have a 5.8 micro amps to amps. So micro is smaller units to begin with, so we're going to use division in here. So what you have to do when you want to do this kind of in calculation, what you have to do is you have to know the conversion factors between this kind of numbers. So for example, for this one we have 3.2 kilometers, 3.2 per kilometers times we're trying to change the millimeters, so we have to know the relationship between the prefixes and the units. So 1,000 1 kilometer is equals to 1 meter, and 1,000 sorry, yeah, 1 kilometer is equal to 1,000 meter, and 1,001 meter is equals to 100 centimeter times 1 centimeter is equals to 1 millimeter, 10 millimeter. So notice we have these units like this because it can be easily be cancelled. So now when we do our calculation, we can go this one out to be out, this one's out, this one's out, and we're left with this one. That's a unit that we're trying to convert. So in doing calculation, we have 3.2 times 1 times 1 times 1 is 3.2 divided by this that will be 1. We are gonna have 6 zeros, 3 6. So our answer is 3.2 times 10 to the power of minus 6 millimeter. Sorry, I made a mistake. So we'll see. The idea is there, but we have 1,000 meter divided by 1 kilometer, so that we can cancel out in it. We just send this one up. That's 100 centimeter divided by 1 meter, and then we have 10 millimeter divided by 1 centimeter. So we just have to cancel it out. So we have something like 3.2 times 10 to the power of 6. These are 6 zeros. So now our answer is 3.2 times 10 to the power of 6 millimeter. Because after cancelling all the units, we have this one remaining. Yes. The second example is smaller unit to begin it. That we have 5.8 microamps to amps. So we divide 5.8 times 10 to the power of minus 6 amps divided by micro is 10 to the power of 6, so 1 times 10 to the power of 6. So this one's out, and we have 5.8 amps. Yep. Yes, basically when you convert from one prefixes to another. In my future videos, I will basically go conversion factors for measurement of length, measurement of time, and measurement of mass. And there I will go through this conversion from smaller to bigger so that you will have fair ideas. Okay, the last part is significant figures or sig fig. Okay, what is significant figure? The number of significant figures in a result is simply the number of figures that are known with some degree of reliability. So the key term is reliability. For example, the number 13.2 is said to have 3 significant figures. So that's like the reliability. It has three numbers for this measurement. Oh yeah. So that's reliability. Okay, there are rules involved when we want to identify or deciding on number of significant figures in a measured quantity. So the first rule is all non-zero digits. So that's a key term here. Non-zero digits are significant figures or sig fig. For example, if we have 1.234, then we have 4 sig fig SF, or sig fig is the same. And another one is when we have 1.2, for example 1.2 gram, then this one we have 2 sig fig. Okay, the second rule says zeros between non-zero digits are sig fig. For example, we have 2.007. These are sandwich zeros, or these are zeros between these two non-digits, so they are significant figures. So we have 1, 2, 3, 4. We have 4 sig fig. And another example is if you have something like this, 2 and 7. These are sig fig. All these sandwich zeros are sig fig. Zeros between non-zero digits. These are non-zero digits, and those zeros between it are significant. So we have 2, 4, 5 sig fig SF. The number third rule says zeros to the left of the first non-zero digits are not significant. So if we have 0.0000005, then if you ask to find the significant figures for this one, then the rule says zeros to the left of the first non-zero digits are not sig fig. So this is the first, and then these are zeros. So we have only one significant figures, SF. This one are not significant figures. Or we can have like 0.002. Then these are not significant figures because they are to the left. So that's we have one sig fig SF. The fourth rule says zeros to the right after decimal point are sig fig. So for example, if we have 2.5000, then they are sig fig because it's after the decimal point. So we have 2, and they are to the right. So we have 2, 4, 5 sig fig SF. 5 significant figures. Oh, when we have 250 25.00, then we have that after the decimal point, and they're to the right. So we have 5 sig fig SF. The fifth rule, this is the fifth rule. The fifth rule says when a number ends in 0 that are not right of a decimal point, the zeros are not necessarily sig fig. So for example, if we have this, like if we have this, then these are just number that end, but they are not right of, they're at the right, but they're not after decimal point. So these are not necessary. But if you want to put it in, if a question asks us how many significant in there, then we have, yeah. So that's the first rule. It says when a number ends in 0 that are not to the right of a decimal point, the zeros are not significant figures. So if we are given this number, this, and if you ask how many significant figures are in here, then it only 2 SF. It's only 2 SF, 2 significant figures. But if we 1.200, 1.20 times 10 to the power of 1, 2 times 10 to the power of 3, then we have 3 SF here. The important is the zeros are not necessarily sig fig, depending on if only we put a decimal point in here, write it in significant form, or if we have like one, yeah. So that's that. So that's the end of the video, and subscribe so that you won't be missing out. If you're confused, or if you need further explanation, then feel free to leave comments down so that I can help you. Yeah, with that, thank you. So to recap, we covered scientific notation, significant figures, and conversion of units. Yep, that's all. Thank you for watching.